Oh, did you do the?
All right, so that was chapter 4, Loiza.
Oh yeah, that was the chapter 4 from the textbook.
All right. Okay, so that's, you just asked me about number 9, okay. Start out with any questions. I believe Loiza has some, but that doesn't mean others can't step in. Or, if you have complete understanding, excellent. That's what a lack of questions means, right? Complete understanding. Loiza, did you have another question?
Oh yeah, there were some more. So
Yeah, I was just filling the gap with pattern. I mean, chime in when you're ready.
yeah, I mean for 17, I was also having some trouble.
All right, so let's take a look at, this is chapter 4, problem 17. So it's the tug of war problem. 2 teams, 9 members each, engage in tug of war. First team member says an average mass, yada yada, and they give some stats. All right, so first off, I'm gonna draw a very simplified, just 2-person tug of war. All right, so this is a rope, not just really long arms. They're pulling on the rope. So if we did a force diagram here, what are the forces?
We have weight acting down on both people.
Okay.
So down arrow in that direction, and then, yeah. Then we also have normal force acting in the opposing direction, so up on the person, down on the ground.
Up on the person, down on the ground. So Y2, 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 so Y1. Okay.
And we have tension on the rope, so acting in opposing directions that way. It's like,
At the ends,
yes,
So-
so,
like that.
and then,
So tension, tension. So one thing in this problem is the fact that the rope is ideal. So we are assuming it's the same tension throughout, and that's pretty legitimate, pretty legitimate approximation to make in most cases. All right? There's something else involved.
Yeah, so it asks us to find the acceleration.
Yep.
And then it asks for us to find the tension. But I was having trouble on getting the tension.
Yeah, all right, so, but in order to figure that out, we do need to figure out, there's another set of forces that we've ignored.
is there
Oh.
friction?
Is it,
Is there friction?
where would that be?
Like acting on both of the people, like, well, no, that doesn't really make sense, cause gravity and normal force would keep them in place.
No, I
Well,
do
if
think
Yeah,
it would be.
wouldn't
If
it-
it's asking us to find acceleration though, then would we assume there's friction? Cause if there was acceleration but no friction, it would be moving, right?
So,
Well, there has to be a force on, acting on the people, assuming, I mean, they are probably moving, but like, if the forces have to cancel out with the tension, right? Like you have the normal force and the force of gravity acting in the J half direction. But I think you would need, another friction force, right?
yeah, I'm fine calling it friction.
Like
Well-
how much they're pulling and therefore how much they're
Ooh.
pressing into the ground with their feet, right?
You're in the ballpark.
Okay.
some of the wording's off. Jacob, you were about to say something.
Oh, I was just gonna say, there would be friction between the feet and the ground, in the opposite direction, where the force of tension is more on one side.
Oh yeah, dad's sled problem, where the like foot was like that way and friction was that way.
Alright. Yes, and you do a long bit, and I'm going, yeah, well, most of it's right, but then there's this little bit I want to nitpick. So, yeah, the spirit of what's being said is right. I want to point out one other thing here, is that if we look at this, just the left-hand side here, right now we have 3 forces acting on the object. So if I said we have an object here where the vertical forces cancel each other out or neutralize each other, which way is this object going to accelerate?
Right.
Over here, which way would that object accelerate? So if there's nothing holding them in place, if there's nothing else involved here, that means that both groups are going to suddenly accelerate towards each other.
So we need friction to.
So otherwise, it's not really tug of war. Now, you can set this up and come up with a near frictionless situation. If they were on ice and they both pulled on the rope at the same time, they would slide towards each other. However, which might make an interesting way of playing tug of war on ice. Surely it's been done somewhere. But the object is, the team that wins is not the team that pulls the hardest, because the tension in the rope is pretty much the same on both sides. It's the fact that if this were a flat surface, there is a friction acting back this way. And over here, there's a friction acting back this way. The team that wins is going to be the team that exerts the greater force on the ground. Now, right now, we're calling it friction. If it's a flat ground, in reality, I've never done tug of war on a really flat ground before. I've always been able to dig my feet into the dirt, so there's a little bit of a normal force there too. Because in reality, the foot's like that. Pretend that's a foot. And so you dig your heel in, and you get a little bit extra ability to stay in place. Or if you want to win, they show you how to do it in Squid Game.
I was about to say, I just watched that over fall break.
That's an uplifting story. If you watch Alice in Borderland,
No, I have not.
that's a similarly uplifting, except the Squid Game Korean, Alice in Borderland Japanese.
Cool, I might have to watch it.
All right. So now back to here. 2 teams, 9 members each. So each of these people now represent 9 people. First team has an average mass of 68 kilograms. So 9 people at 68 kilograms. Exert an average force of 1,350 newtons horizontally, 1,340 newtons horizontally per person.
It said 1350.
To 50? Okay. I think I just said 15 as I was writing 40 down. It happens. All right. Second team, 73 kilograms. And 1365. So magnitude of the acceleration of the 2 teams. There are a couple of ways of approaching this. I'm going to take this a much more methodical way. I'm going to skip some shortcuts and do other ones. But if you've got a faster way of doing it, more power to you. Go for it. So what I'm primarily concerned with are the 2 teams. So I'm going to do my equations of motion based upon them. I guess. Force diagram done. Which way are they going to accelerate?
I'm assuming this way.
So right now I've had answers in both directions. Oh, going to that way?
Wait, oh, yeah, sorry, that way,
Yeah, that this,
because that's more
Would be
force
better.
and they weigh more, so, yeah.
and it's not the mass that's as important as the fact that this force right here is the key thing.
Yeah.
Now, there might be a relationship between this force and their mass, but at this point in the problem, that's irrelevant, given this. All right, so acceleration, we're gonna assume is this direction, so we'll make that the positive direction. Coordinate system, right there. Coordinate axes, nothing to decompose, everything is nice and parallel, anti-parallel, and perpendicular. My equations of motion. So I have F2 minus friction 2 minus tension is equal to mass times acceleration, so mass 2 times acceleration. Then we have Y2 minus W2 equals 0. For the other one, I've got tension minus the friction is equal to mass 1 times acceleration. And then Y1 minus W1 is equal to 0. I am making the assumption that both groups have the same acceleration. That one group is not gonna suddenly just let go of the rope. If one group did decide to just let go of the rope, then my accelerations are different, and so I'd have a subscript there. So now we're trying to find acceleration, so right here. So we have F2 minus F1 is equal to M2A plus M1A. So F2 minus F1 is equal to M2 plus M1 times A. Or my acceleration will be the net force here divided by the total mass. There's one other thing you have to remember when we plug in numbers, but before we get to the number plug-in, questions about how we get well to here.
Yeah, so I get how, you did it so that like, I see how you came up with the, first part of your equations, but but like, why does sum equal 0 and why does sum equal M2A and M1A?
Because we're still assuming that Newton's second law is true. That the total force is equal to mass times acceleration. And you can even break that down into perpendicular bits. The horizontal force is equal to mass times the horizontal acceleration. Vertical force is equal to mass times the vertical acceleration. Well, I'm assuming that they are only going to be moving horizontally. That vertically they are staying at this exact same level. They're not coming off the ground, they're not digging into the ground. So therefore, since this is vertical here, that, I guess make off positive. Since this is vertical and there's no vertical acceleration, or vertical acceleration is 0, so technically this is mass 2 times 0. So some are equal to 0 because acceleration is equal to 0 in that direction.
Okay, that makes sense now.
And again, we tried to set up a coordinate system so that that's gonna happen.
So when you're actually solving for A, when you're plugging in like F2, would you multiply the 1350 newtons times 9 since there's 9 people?
Yep.
Okay.
Why did you subtract Ft from F2 rather than F2 from Ft?
Established gut feeling is that the acceleration is gonna be to the right. And so I made to the right positive. And over here, my F2 is in the positive direction, my tension's in the negative direction. That's why I did F2 minus Ft.
And then why is it Y2 minus W2?
I had not written that beforehand, but, I made up positive. Maybe make that I hat and J hat. I could have made down positive just as easily, and that would just been W2 minus Y2.
And then when you start writing in green, the reason why FT isn't there is because those two forces cancel out, right?
Right, when I just add them straight up, I got a negative FT and a positive FT.
Right, so it just cancels out.
And the math tell me that adding those together, you get 0. And again, if the math people are lying, then
Then what are we to do?
yeah, the whole course and most of my life is gone right there.
Wait, so you said that the second one and the last one cancel out?
No, when I added the first and third equations together, I have this F2 minus FT here, and then I have an FT minus F1 here, and the tensions canceled out.
Oh, yeah.
Technically, what I've done, when I add them, I get F2 minus FT plus FT minus F1. That's just adding those together is equal to M2A plus M1A. And this go away.
Okay.
So, the plugging of numbers in, as I think Jacob mentioned, this is the force per person. So technically this, our F2 is that times 9. M2 is that times 9. M1 is 68 times 9. And F1 is 1350 times 9. So, as it turns out, each of these terms here, we're multiplying times 9, so we could just do it per person, or you could multiply times 9, whichever way you like. So, 1365 times 9 minus 1350 times 9 over 73 plus 68. So if we multiplied it all by 9, the 9s would cancel out. $41. Feels right, unless I wrote one of these numbers down wrong. Nope.
And that's equal to our acceleration?
Pardon?
That's equal to our acceleration?
Yes. For the fraction fans. Actually, if you're going for fractions, why bother reducing?
Wait,
No.
if you do the top part, if you do 1365 times 9 minus 1350 times 9,
Right? You get,
oh wait, yeah, never mind, I punched it in my calculator wrong. I got it.
Wait, so can't you also just do the F equals MA?
that's what we did to get these.
Yeah, but like, I'm saying like, instead of going through, the equations of motions and everything, like, couldn't we have like found the net force and then the masses and just solve for acceleration?
Yeah, you could have, that's one of the shortcuts you could have taken.
Okay.
If you treat the whole thing like a system, instead of treating each person individually and the rope as an individual thing, you could have done the rope and the people as one thing and look at the you basically have 1365 times 9 and 1350 times 9. So the difference divided by the total mass. Yeah, you could have done that.
Okay.
One of the reasons why this has a slight advantage in this particular case is that the second part, when you ask to find the tension, you need to do this at some point anyway, to find tension.
Okay. And I'm just wondering, like, why did we choose the one on the right? Is it because, like, that's where it's gonna be headed?
Oh, why do we choose to the right positive?
No, the right person, like, the person on the right.
Why do we choose that as the 1365?
No, like, why did we choose, like, him to do the, well,
Oh,
to do
for the equations?
Yeah.
Well, we did each person. This is that person right there, and this is the other person, or
Oh,
people,
okay.
team.
Okay.
Basically, you rarely include the ground in the equations of motion. Because we generally deal with problems which deal with things that are moving relative to the ground. The rope has no mass, so you ultimately would end up with whatever's on the left side is equal to 0 times acceleration. So the rope is ideal, doesn't have much of an impact. So it basically leaves you the two people.
What if the rope had mass?
If the rope had mass, then the tensions would not be the same.
Okay, so we'd have to have tension for either side or just tension in general?
We would have, this would become FT1, FT1, FT2, FT2. And so we'd have another equation over there of FT2 minus FT1 is equal to mass of rope times acceleration.
Okay.
We'll eventually get to something like that, but not yet.
I didn't doubt it, I was just curious.
Then,
Is y2 minus w2 always 0, or
no, not always 0.
when is it not 0?
If we had an object falling, and that would probably be one of the equations with an actual acceleration, and then horizontally there probably wouldn't be acceleration.
That is a case right there. A case where the weight of an object or normal force acting on it. So right now, this book has a weight on it because of the gravity. The weight doesn't change whether I touch it or not. But the normal force between the table and the book is definitely not equal to the weight. But there's another normal force. So now I have 3 forces involved in this that would add up to 0. Or sort of doing the reverse of what Brooke was saying as I lift it up. And that's a case where the normal force and the weight are not the same for part of that cycle back and forth.
Wait, were you giving an example of when you were pressing down in the book that the the vertical acceleration is not equal to 0?
No, that was an example of where it's not just 2 forces
Oh,
adding up to
okay.
0. That would be 3 forces.
Okay.
When I was moving the book up and down, that's a case where 2 forces acting on the book do not add up to 0.
Right,
Okay, yeah, thanks for clarifying, because it's like, what? I was confused.
And so if tensions cancel out in that, then how would we ever be able to find tension?
Because now you look at the individual pieces of it. So in the second part, just double checking, yeah, what's the tension in the rope? Once I know the acceleration, I now know this. They give us the mass, they give us the force. Friction's or tension's the only unknown. Or we could come down here. We know that, that, and that. Solve for it here. Or
Okay.
we could do it both places, and if we get the same answer, we should feel pretty good. If we get different answers, then that's up to you what you do next. What you probably should not do is write down both answers and go this or that.
I've done that a couple times.
Yeah, well, that's, not the only one.
I just wanted to include all of my thought processes,
If you do that, I should say, if you do that, if you want to say it's this or this, go, I know something's off here, they're supposed to be the same. Something like that, just to make me feel better.
Yeah. I think I did write that in one of my labs. I said, this is wrong and I don't know why, and then I turned
Oh,
it.
okay, so that was yours, okay.
Yeah.
Yeah. I did appreciate that.
I mean, I'd rather be honest with you than just write down an answer I know is wrong.
So to find tension here, we have 9 times 1365 minus the tension is equal to 9 times 73 times 5/47, assuming I haven't made a mistake down there. Or tension minus 9 times 1350 is equal to 9 times 68 times 5/47. This time the 9s don't cancel out, and so you definitely need to have them in there. And then the tension mounts to find out whether those tensions are the same.
Why is it 9 times?
Because there are 9 people on a team. The numbers that they give, the 1350 and the 68, the 73, the 1365 is per person. Part of it is I didn't feel like writing 9 people up there.
Doesn't matter, like you don't say 9?
It matters here, it doesn't matter over there, but it does matter over here. Because the tension is a single number, it's not per person, the tension in the rope is there because of all 9 people. So it's sort of a cumulative effect.
So, I'm just making sure, there's 9 people on either side.
Yes,
Left side is 68 kilograms
Per person.
individual, per person,
on average,
and then 73 is, per person on the right.
correct.
Okay.
Well, I got very different force tensions for each of those.
Did you? Jacob, you scratching those, you also got something different?
What did you get?
He guarantees right, but for the first equation I got, 12,215, and for the second equation I got 186.
I
So
got,
you got for the second one?
I got 12,215.
Okay,
For,
did you get something for the
I
second
didn't do
one?
this,
The
I just did
second
that one.
Yeah, the
I haven't
second
done
one
both of them.
Did you get 186.6?
No, for the second one, I added 12,150 to the other side, and I got 12,212. Which is a lot closer.
Yeah, that's what I got too.
Okay.
I got both
No,
of those numbers.
I didn't do the first one, I just saw the second one, I was like, okay, I'm gonna do this.
somewhere there's a small little error.
Oh, you know what?
Could be decimal.
The 215, I think I substituted, I think I put 1350 in where I was supposed to put 1365. Or wait, did I?
I think you've come up with a very different number if you've done that. Well, the spirit of what we've done here is correct, but the numbers we're working out right now are not.
I got the exact same answer.
What'd you get?
12,215.11.
You're getting this for the second equation as well?
Yeah, both.
Okay, I'm just typing something wrong, I guess.
It might be, I don't know, this might be my calculator, but every time I put in a fraction, I have to put in parentheses, otherwise it
Yeah,
multiplies the
that's
first and then divides.
Which
But-
actually should not be an issue here since there's no addition or subtraction.
Yeah. What'd you get for that? I got like, I multiplied 9 parentheses 68 parentheses 5/49, and it gave me 60.
47,
There you go.
it's 47.
Oh, I saw 9, that explains
Looks nothing like a 9.
it. See, okay, now I got it.
Okay. Alright, so it looks like we've narrowed down on the answer for the tension. Oh. There it is.
So even if they weren't the same, what if they were extremely similar? Would we be able to say that our acceleration is correct, or?
Odds are, yes. If I've given you a problem rarely will someone get close to the right answer by doing it wrong, but it does happen occasionally.
Okay.
So if you ever ask us for the tension, this is how we'll do it. And we should probably double check by doing both equations, right?
That would be ideal, but I also know that if you do both of them and you get different answers, then you're stuck with
Okay.
where's the mistake?
Yeah.
And then it comes down to how do you actually deal with that?
Ah, I got it,
Okay.
Yeah, they
simple math here.
the same.
For me, whenever I have to redo a problem, it's better for me just to start from scratch,
Yeah.
as opposed to try to follow my logic, because
Yeah,
I
same.
rarely find my mistake if I'm doing that.
Yeah, and start over.
It's funny you say that, cause 2 weeks ago I was doing a problem for an hour, trying to figure out what I did wrong, and I picked apart like different parts of the problem. And finally I just got up, I was so frustrated, I just walked around the house for a second, and then I sat back down and rewrote the entire problem, and I got it on first try. I was like, what am I doing?
It's the talent to know when to stand up and walk away
Yeah.
that I lack
There's
sometimes.
absolutely nothing like being frustrated with a math problem. Like, it is the worst frustration ever. One time I like got up and went on a walk, like a whole walk, music and everything, because I was so over this math problem I was doing.
But think how good it feels when you finally get it right.
Yeah.
Like banging your head against the wall. Feels good when you stop.
Well, the problem is, I'd feel good when I'm done with the whole set. So once I'm done with one problem, I'm like, another problem exactly like it.
All right, bringing it back down to physics. Any questions on this lovely problem? Poison, did you have another question? Or does anyone have another question?
I mean, well, that's it for 17. Like, there's like 4 more, but I'm just gonna ask you once class is done, so we can, do lecture.
All right, I'll follow your guidance on this one. You sounded like you wanted to wait and ask the other ones later.
Yeah.
Okay, I'm fine with that, or if anyone else has a question, I can take those too. As well as on Friday before the quiz, I'll see if there are any questions.
So if they gave us the friction S and friction K, then how do we find the acceleration?
So if they gave you Fs and Fk, they'd have to give you slightly more information. Usually in a tug of war, depends on how this group is actually moving this way.